This is the well pump. Now we will discuss how to draw the mechanism diagram and then the loop closure equation of the mechanism. How many links are there in this? How many
4 links.
links? It's a four links. See here which are the four links. C is one pair, B is another, A is another pair, and there is a bucket or there is a slider inside this cylinder. So one sliding pair is there. That slider is going to act as a bucket which carries the water from the well. Okay, that bucket is going to deliver the water from here. So that bucket is going to reciprocate inside the cylinder. So from the kinematic point of view, that bucket and the cylinder pair is the sliding pair. So that pair, that cylinder or that bucket, that you can represent here itself. See here, the first is this link. This is the handle. The line joining A and B is the handle. Line joining B and C is the, you can say, connecting rod or the oscillating link. Then the piston, because this dimension has a no meaning. This from C onwards to up to the cylinder, there is no meaning. So here itself you can show the piston. Yeah, this is the piston, and to have the cylinder location, cylinder is there outside this. That keep the hatching line here. So this hatched line indicates it's a cylinder. So piston one link, this connecting rod second, and this handle is the third. And what is the role of this vertical? This vertical is not moving, it is a fixed link. The vertical is a fixed link, it is a completely a fixed link. The role of this link is just to maintain the height of this handle, to have the, for the operational point of view, to have the easiness, this height is been maintained by fixing this, giving this support. So this is a fixed link. So it's a fix. This is a fix. And this distance, the distance between, if you see the line of reciprocation of the cylinder is this. Line of reciprocation of the cylinder is this vertical line, the center line. This is the line of reciprocation. Right, this is the line of reciprocation. You can represent that as a center line, the center line. And the role of this horizontal line, the horizontal distance, this distance, it is like a offset slider crank mechanism. See here, so this is the fix. I'm writing this as D point. This point is the D point. Now look at the loop of ABCD. Look at the loop of ABCD. It is a closed loop. In this loop, this is also going to work as a fixed link. This one, the CD distance, is it? It is going to remain fixed. What is going to change? Yeah, how you will write the, yeah, this dimension is going to change, vertical dimension. because as the piston slides inside the cylinder, this distance is going to change. So in another way, I can draw this diagram for the understanding purpose. See here, AB, CD, AB, BC, CD, and the ED. This is called as a offset slider crank mechanism. You may think like this. Okay, this is the mechanism. This is taken this way. Okay, then something is like this. You can easily understand now. This point is this is the fix. This is a fixed cylinder. Now your crank is here, and this distance. This is the this dimension. Now this point is the A. This one is A. This point is B. This point is C, and this point is D. Okay. Now, when the mechanism moves, this is the axis of the cylinder. Axis. This is the axis. Okay, in this direction, it is going to reciprocate. So this distance is going to vary. But if you look at the a loop of this mechanism, EBCD is the loop. In that, CD is a constant distance, that is 200. DA is, that is a variable distance. As the piston, what is the DA? The DA is nothing but the distance between A and C. Suppose the C is came here. Suppose the C is came here, then you have to take DA. C is not, DA is nothing but this one. When the piston is came here, this distance is going to act as a DA. So that way, the DA is the variable. Just for the understanding purpose, yeah, this is a horizontal line. AD is the horizontal, vertical line here. In fact, I can write the loop closure equation like this. Give the numbers to the link. A number, this is 1, this is 2, this is 3. Okay, and this is the 4. This is a 4 loop. What we are given, this fix is 1. Okay, this is, even though it is a fix, it is going to vary in your loop closure equation. This point is 1, this handle is 2, this is 3, and this is the 4. This is a 4. Now right here, the dimension of this is R1. Dimension of this is R1. When the slider changes its location, R1 is going to, this distance is going to change. This distance is going to change because the location of D is with respect to the C point. As the C changes the position, D is also going to change the location. So like that. So we are assuming the R1 is a variable, and change in R1 with respect to time, that is the velocity of this link. Are you getting? So here some common sense, common logic, the basic understanding is required. Even though, because this variation of piston C is mapped with this fixed link, even though it looks like a fixed link, but the distance is distance with respect to C. The distance between A and C is going to vary on this link. So R1 is kept as a variable. Now this dimension is R2. This dimension is R3. This dimension is R4. Okay. So how much is the R1? R1 is the question mark. It is unknown. R2 is how much? R2 is 250.
250 mm.
250. R3 is 300, and R4 is 200. R4 is 200. These are the constants. So writing the loop closure equation is to identify the mechanism and its loop. We identified the mechanism as a slider crank mechanism, and its loop is like this. The loop is obtained like this. Now write the vectors, and before writing the vectors, you may take the arrows, represent the arrows for every link or the every sides of the loop. This is like a rhombus. It is a polygon of the four sides. So each side to be represented as a vector. So for that you need to show the arrows. So I may take the arrows for this is from this direction, upward direction. The arrow for this is like this. Okay, arrow for this is like this, and arrow for this is like this. Then the angles, as we discussed how to take the angles for the each vector. Arrows to be measured at the tail of the vector from the positive x. From the positive x, the arrows to be measured, the angle to be measured at the end of the vector. This is the vector. Here its name is capital, yeah, capital R1 bar is the vector name. This vector name is capital R2 bar. This vector name is capital R3 bar. This vector name is capital R4 bar. Okay, now measure the angles from the positive x. This is the positive x. The angle for this, this stands for theta 1. From positive x, this is the positive x, right? From here to here, this is the theta 2. Okay, for this horizontal line, horizontal line, are you getting this?
Yes, sir.
This is a horizontal line, and from the horizontal line, peg this as theta 3, and this is theta 4 from the positive x. Theta 4, theta 4 is here. Theta 4, theta 4, because this line is mapped with the positive x. Theta 4 angle is 0. So write down the values of these angles. Theta 1 is how much? Theta 1 is 90, right? Theta 2 is, theta 2, is it how much? This theta 2, that this direction is 15 degree, it is given, no?
195. 95 degree.
95, or how it is 95?
195.
295, right? बरोबर है का? No, it is a 295.
195, sir. 100.
Ha,
195.
195. Yeah, this is 195. Theta 3, theta 3 करता येईल का नाही? You may put a question mark on theta 3. Theta 4 is a 0. So in this data, R1 is unknown and theta 3 is unknown. Only two unknowns are there. So you may get these R1 and theta 3 by solving the loop closure equation. And you keep in mind, suppose if from this data, if more than two quantities are unknown, then even by solving the loop closure equation, you will not get that quantities, because after solving the loop closure equation, you will get only two simultaneous equations. That means you can get only two variables or the two constants. If more than two variables or the two constants are unknown, then better to draw the mechanism diagram in a dimensions on a paper by following the concepts of geometry, and from that figure you can get the unknown quantities. So instead of going into the complex things, again some iterations and so on, better to get the unknown quantities related to displacement variable, the dimensions, from the figure itself. Basically we want to see the velocities and acceleration. If two unknowns are there, then just solve the displacement equation or the loop closure equation, you will get it. But if more than two unknowns are there in a displacement equation or the loop closure equation, better to draw the mechanism in a proper scale and measure the variables or the constants from the figure. So before going to the displacement velocity and acceleration analysis, you should be known all this variable, all this variable and the constants related to dimensions and the displacement variables. So in this equation, in this system right now, we see that only two unknowns are there. That means we can get these two unknowns from loop closure equation, from the solution of loop closure equation. You need not to draw the figure with the proper scales. Need not to draw. So this freehand sketch is sufficient to go ahead. So this way, this initial judgment is very important. If three unknowns are then and you are go on solving the equations, then you may land in a very complex situation. Nothing is getting out of these equations. Only two equations, three unknowns. How to solve that? I can go with the iterations, trial and error, and so on. Not required. Better to draw the figure. Okay, now come to the loop closure equation. Uh, I have shown all these arrows in a same loop. This R1, R2, R3, R4 are on the same loop. So this will be the equation directly. R1 bar plus R2 bar plus R3 bar plus R4 bar equal to 0. R1 bar is R1 e raised to I theta 1 plus R2 e raised to I theta 2 plus R3 e raised to I theta 3 plus R4 is theta 4. Yeah, this is the LCE, loop closure equation. See, in this R1 is unknown and theta 3 is unknown. The rest of the quantities are known. Solve this for theta 3 and R1. Okay, so after solving this, you can understand all the constants and the displacement variables at this stage itself. After this, go for the velocity, differentiate this equation. Yeah, differentiate this equation, differentiate with respect to time, with respect to time. Okay, for the velocity, how the equation will come. So you are going to solve this equation for r1, this one, and theta 3. You will get that. Now see here, differentiation with respect to time. What will come? What is going to change here? The theta 2 is going to change, as when the mechanism is in operation, theta 2 is going to change. So d theta 2 by dt is the omega 2. Theta 3 is also going to change. D theta 3 by dt is omega 3. Theta 4 is going to remain constant. It is not going to change. Theta 1 is not going to change. It is constant. Theta 1 is a 90 degree. It is constant. Theta 4 is also a constant 0. So in this case, while you take the differentiation mechanism to be seen properly. Theta d theta 1 by dt 0, d theta 2 by dt, what is this? Omega 2. D theta 3 by dt This is omega 3, and d theta 4 by dt, it is 0. Again, this angle is not going to change. The next is R2, R1 is the dimension. This is going to change. R2 is constant, R3 is constant, R4 is constant. Only this is going to vary. So dr1 upon dt, you call this as the velocity of this piston, velocity of this piston. So that should be a Vc. Can say velocity of piston, Vc. Yeah, this understanding is also important while you take the differentiation. So what equation will come now? Here. Now both the d theta 1 by dt is a constant. So only r1 is going to vary. So e raised to I theta 1, this is Vc now, velocity of piston, plus r2 I, r2 I e raised to I theta 2 into omega 2, plus r3 I e raised to I theta 3 omega 3, plus r4 theta 4, both are the constants. So it's a 0. This is equal to 0. So this equation is called as a velocity equation. Velocity equation. Now look at in this equation what is known. Yeah, are you getting this? What is known and
Yes, sir.
what is known and what is unknown? Vc is the unknown and omega 3 is unknown. Rest of the things are known. Solve this equation for omega 3 and Vc. I hope you are understanding the solution part of this equation. Expand this equation by cos theta I sin theta term, and then separate out the real and imaginary part. Equate the RHS and LHS part of real and imaginary. That way you will get the two equations and the two unknowns are there. Solve that simultaneously. So the solution of this equation, you will get Vc, velocity of piston, velocity of this bucket, water carrying bucket, and the angular velocity of this connecting rod. I think some velocities are given. For what it is given? Uh, Figure shows the primitive wall pump that is a common in undeveloped areas. To maximize the water flow, the piston should travel at upward. Yeah, the piston velocity is given. The piston velocity is given. See here. Yeah, this VC is given. VC is given. That is the input output quantity is given. Sir, omega 2 and omega 3. To reciprocate that piston at a particular speed, what is the velocity of this link and what is the velocity of this link? That is to be determined. So in this case, the VC is known, omega 2 and omega 3 are the unknowns. You have to solve this equation for omega 2 and omega 3. Now to have the acceleration, take Differentiate that equation again with respect to time. Yeah, differentiate this equation again with respect to time. Yeah, this one. And again in the differentiation, what things you need to put? See here, Vc is variable. So dvc, the acceleration change in the acceleration of piston with respect to time, you call as fc, acceleration of piston, linear acceleration. Omega 2 is going to change. So omega d omega 2 upon dt, you call this as alpha 2 angular acceleration because that is a oscillating link. Then d omega 3 by dt, this is alpha 3. Vc is changing, r2 is constant, theta 2 is changing, r3 is constant, theta 3 is changing, omega 3 is changing. So see here how this will come. Again this will come, this term is only one variable, that is Vc. So Fc e raised to I theta 1 plus, here omega 2 is variable and theta 2 is also variable. So you can write this I R2 in a square bracket you can take, or you can, yes, omega 2 e raised to I theta 2 e raised to I theta 2, then this is I, then again d theta 2 by dt, one more omega will come, and that will become omega square plus, the UV rule is applied here. Here alpha 2 e raised to I theta 2. This is the expansion of this derivative of this term. IR2 common, then first taken the derivative of e raised to I theta 2, omega 2 is here, then second time taken the derivative of omega 2 and this. Then similarly I R3 square bracket omega 3 square I e raised to I theta 3 theta 3 plus alpha 3 e raised to I. Yeah, this is equal to 0. Yeah, are you getting this equation? Look
Yes,
at in
sir.
this what is known and what is unknown. Fc is known, alpha 2 and alpha 3s are unknown. In this case, the acceleration of piston is given. 150 is acceleration of piston is given. From that, you have to find out acceleration of handle and the connecting rod. So these are the equations involved in the solution of this wheel pump problem. I hope all of you are getting this. Yeah, this is equal to 0 here you can put, and this is the acceleration equation. Solve this equation for alpha 2 and alpha 3. So this is the methodology for getting the answer of this well pump.